Okay, for those who are joining us for our 1 o'clock scheduled start, this is what happens when you try to do things live. You come into unexpected things, but it's mostly about our AV feed. We're trying to do a few things simultaneously and trying to get a live feed of the test stand and what we're showing you here today about um, grease optimization using some ultrasound sensors combined with auto lubers and talking about grease analysis as well. So just stand by for a few minutes. We're live streaming this on YouTube as well. And we get this squared away, and Sloan gives us the heads up that we're good to go. Blair and I will kick this off and talk about this topic with you here today. Blair, maybe we can get started just giving a little bit of background. What do you think?
I think we can.
Super. So introduce yourself for us as our guest today on Grease Thief Thursdays, a little bit about your background and what we're going to talk about today.
Sure. Well, that should take about an hour, and then we'll have a few minutes at the end for the demo. So my name is Blair Fraser, as Rich mentioned, from UE Systems. I'm on the sales and technology side at UE Systems. And if you don't know UE Systems, we're a global provider of ultrasound solutions in the industrial ultrasound market, and we manufacture and go to market with our own equipment. What we're talking about today is the on-track system, which came out a couple of years ago, and I'll give Rich and the team at EPRI that worked on it credit for kind of starting this process around combining some kind of condition monitoring to these auto lubrication devices. And at UE Systems, we really see an increase around ultrasound guided or condition based lubrication in the market, and I'm sure you're seeing that as well, Rich. So if you go back into our history of 50 years in the market, ultrasound is traditionally being dominated by leak detection. And it's interesting to see over the last decade or so that focus is really starting to shift, and our market is shifting from leak detection, which is still a great use case and often pays for a handheld instrument in itself. But we're starting to see more and more people move away from time-based lubrication and move over to condition-based lubrication. And as for my background, I've been in maintenance and reliability for 20-something years. I did start off as an end user, and I jokingly say that if I was to go back in time, I'd have to apologize for any company I worked for that I lubricated their bearings, because I 100%, without a doubt, no uncertainty that I lubricated them improperly. So those bearings that I did lubricate back when I was working in the field undoubtedly have since failed. Not during my tenure, but they did fail. And then I did work in a few industries, oil and gas and pharmaceuticals, and then I switched over to the technology side and spent the rest of my career there.
Nice. And hey, we've all learned the hard way from time to time coming up through the ranks, and I'm no exception to that, but we won't share all those stories here today. But it's good to kind of take some time and reflect to where we are now and what we've seen as new technologies, beneficial ways of applying those technologies. And yeah, for something that Mike Johnson and I just envisioned as part of an EPRI study some 10 years ago or so, which was, can we tie these things together? Can we tie ultrasound with the delivery of grease? It was really cool for me to see you guys, kind of taking that and running with it. And that's why we were excited to take that technology and add it to the test stand that we have in our laboratory. So let me go through a little bit about just the background of greasing and things, and then I'll take it into your discussion, Blair, about the technology that you guys developed and go from there. But I'm going to here in the background, I got a little PowerPoint running to stay on with the topic. And we're going to talk about a couple of advanced strategies for optimizing grease lubrication, one being using ultrasound and tying that in with the timely delivery of grease to the bearing being monitored, and the other being what we can learn from sampling that grease and analyzing it and looking at the chemistry and the wear and so forth. So two technologies really that are quite complementary. I'll talk about, or we'll introduce the idea of why bearings fail, due to both over lubrication and under lubrication, and how ultrasound can play a really important role in getting that situation under control for a facility. And we'll talk about the role of ultrasound in delivering grease, like how that becomes a solution for these problems of over and under lubrication. And particularly here today, talk about online sensors and how that can get us into a state of optimal grease delivery with kind of real-time feedback into the process. Then I'll give you a chance to talk more about the kind of problems that can be found in the bearing itself. Once something happens, or a bearing was installed and it had damage, or it developed some damage over time, and how ultrasound can pick that up. Then we'll get into the demo of the test stand and show how these sensors integrated with the auto lubers work. And then we'll crack open a bearing and in the lab and show a little bit about how we use the grease thief sampling kit to pull a sample out, and talk about the analysis that can be done once we have that. But, over and under lubrication, the point is, unless we know exactly when and how much to add, then we are by default over or under lubricating. And under lubrication, we'll talk about both of these. Under lubrication results in wear and damage, and over lubrication can be things like energy losses, overheating, and so forth. I've addressed this in the past in the context of really sustainability when it comes down to it. Sustainable processes towards lubrication, and how the kind of default status or default state of the industry ends up being over greasing, in my opinion. And here's some reasons why. Under grease. So you got you got three potential states. One is, well, you just got lucky and you are greasing exactly how much needs to be there at the exact right interval. Or, maybe you're using these technologies to get you there. But nonetheless, if it's not that situation, if it's not the exact amount that's needed and when it's needed, you're either under greasing or over greasing. If you are under greasing, that means that there's either an inadequate quantity of grease to the location that's needed, or it's being delivered there too infrequently. And so the result of that is machine damage. And machine damage leads to failure and loss of function. So what is the natural human reaction to machines failing and the perception of, or the confirmation of, a lack of lubrication? Well, the response is grease more. And so once we grease more, now we get into over-greasing. And when we have over-greasing, what are the effects? Well, they're machine overheating. They can be cleanliness issues as the grease gets into other areas it shouldn't be. We have the excessive cost of grease. We're spending more to purchase and use grease than we really need to be. There are disposal issues about the excess grease that's there, and then some hidden effects. But I think when you look at all of these, they kind of fall under either hidden or harder to see. It's easy to see when the machine has failed. Everybody's involved. Everybody knows there's noises, there's bangs, and we're not producing what we're supposed to be producing. But when our default is over greasing, it's a quieter situation. It's less obvious and less in need of immediate action. So I would say, from the typical human response and how we operate in most production facilities, is we end up over greasing most of the time. And so that creates then this opportunity to reduce grease demand by moving towards optimization. If we're mostly over greasing and we move towards the optimized state, that's going to save some grease. It's going to move us on that line of sustainability. So this gives us an opportunity to extend grease life, to eliminate unnecessary lubrication, and to raise the awareness of the impact of over lubrication on cost, as well as the impact to the planet, the impact to sustainability of our processes. And so we can actually get into some calculations about what is the, say, carbon footprint or the emissions coefficients of using grease unnecessarily. And there's some calculations that we can do here, and I've gone through some of that, but ultimately we can look at and determine what our footprint is for a non-optimized greasing situation, and actually project what we could do for our company or organizations by moving towards optimization. It involves keeping carbon in the ground when it comes to it, because that's what we're putting into the machines, or hydrocarbons as greases. So Blair, I'm going to put one of the first slides that you gave here up next, and let you kind of lead in this evolution where we talk about, historically how we've done it and how we move to some of the options that are out there today.
Yeah, and thanks, Rich. And that was great. Always hearing the sustainability part. That part always really impresses me. And we are doing some studies around measuring friction and that cost of friction and what that means to increase load and energy and things like that. But as we look at this now, keep in mind this is how Blair sees the evolution of bearing lubrication. It's not exact timeline here, but if you look at when we started lubricating, let's talk about machineries. We started generally with whatever lubrication, and what I mean by whenever, it's just we want to get to it, I'll lubricate. If a little bit's good, a lot is better type strategy, and that still exists in our factories today. And depending on the bearing type and the machine type and the load and all those things, it can serve somewhat okay. But really, what happened over the evolution is companies developed formulas, and there are some standard formulas. There's some different formulas. There's some variants in those formulas, and it doesn't really matter what formula you use. Any of the formulas, at least that I have seen, always has some variables in them that change over time. Speed of equipment, and more we're seeing, particularly rotating assets move towards VFDs, so variable speeds, in lieu of control valves and things like that. So they're starting to ramp up and ramp down the speed of assets based on production demands and things like that. There's temperature. I'm based in Canada, so our summers do get hot, but our winters sure do get cold. So temperature can have a big fluctuation in how much and when to lubricate. So those calculations do have a lot of variance in them. So, and the primary way we were doing that is we're using the calculator to figure out a time-based schedule. And if anything, from what RCM taught us back from Nolan Heaps in the late 60s, early 70s, is that, a lot of things fail randomly, and a lot of things we can't do based on time. So we call it condition-based or route-based lubrication based on condition. And what we did is we still did it based on a calendar, but instead of going around and actually lubricating, we used our technology, our ultrasound technology, and I'll get into it on how exactly it works at a high level to determine when we're doing that route, if and how much grease is required in that bearing. But we're still walking out there. We're still doing it on a time base. Typically, what we see as a standard is monthly, but it depends on the criticality of the asset and things like that. And at the same time, 3 and 4 really came out. In fact, over the pandemic, the amount of use of number 4, in my opinion, just what I'm seeing in industry, really started to increase. And so what happened there is we couldn't get out in industries, or we had to stay home. We had to quarantine because of the pandemic. So the sales of the implementation of these single point lubricators or distributed lubrication system really started to grow, and up for obvious reasons. But out there today, unless you're using our systems, they're still based on time. Now, they did get smarter. I don't want to put down single point lubricators. They're still based on time, but they might have additional sensors on to determine some of those variables. So we might see a vibration sensor to make sure when it's lubricating, it's running, or to account for the time if the machine is off. So they did get marginally smarter. And so what happened over the years, and we've been asking, or our customers have been asking for this, we've been wanting to do this for a long time, but really we're waiting for the technology to come to the point where we could do it at scale and cost effective, of being able to combine the precision and accuracy of our ultrasound guided lubrication devices or sensors, and combine that with the convenience, contaminant free precision of a single point lubricator, and really tie those together. And as Rich mentioned, it's that EPRI study that really proved that it could work. Now, that we didn't have a doubt it could work because we saw it with the route base, but just how we combined it. And the truth is, if you look at it, we've had this on track out for 2 years. We do have a pretty exciting release coming this fall that's going to change the evolution of this slide even further. But even when we first developed this, we learned a lot. We used to see data at a month time interval, and seeing data, down to the second, which we're going to show you live, really changed the way we look at when to lubricate and how much to lubricate, including some added benefits of that as well. So maybe Rich, you can go the next slide for me. So when we look at this, is how what are we doing when we're using ultrasound? And for those that aren't familiar with ultrasound, I'll keep it high level. And if you do have any questions, we can definitely dive a lot deeper into the theory and use case of ultrasound. But essentially, what we're doing is we're listening to things that you can't hear. So we're listening at a frequency, at a very high frequency that even dogs can't hear, right? So this is above that 20 kilohertz. Typically, we're around the 30 kilohertz range is where we try to center our frequency to measure that. And what we're doing is we're essentially measuring that friction in the bearing. And the reason I say friction is because it becomes very simple to understand and use, even as you get up to the C-suite to justify things like this or to explain what you're doing. Friction becomes very easy to understand. Friction is bad. We don't want friction in our equipment. So it's really simple. That's the friction the bearing increases, and it increases for two reasons. One is lubrication. So there's a lack of lubrication as that grease starts to degrade in that bearing. Obviously, that friction is going to go up. But also, we can look at the monitoring side or the health of that bearing as well. So if there's a defect, I don't care if it's inner race, outer race, cage issue, individual rolling element issue, it's all going to produce an increase of friction. And how much that friction increases and what that pattern starts to look like, obviously we can start to do FFTs and look at bearing pass frequencies and things like that, becomes very dependent on the failure mode. So really what we're trying to do here is not only monitor with this system, we're not trying just to monitor the health of the bearing, but we're trying to focus on what's causing about, depending on the study, 60 to 80% of premature bearing failure, which is grease issues or lubrication issues. So this system is a monitoring system, but really where the advantage is that proactive side or that defect elimination side is we're trying to stop that defect from happening in the first place. And if you can go to that next slide there, Rich. So this is an exaggeration. Now this is under lubricated. And I fully agree with you, Rich, that what we see, unfortunately, is over lubrication. And I can tell you back in my history, when I was green, I definitely over lubricated. And we see that all the time. And, I'm starting to see, the messaging around, not over greasing really start to resonate more and more in industry as we attend conferences and things like that. So I think we're heading down the right path. But when we're looking at this ultrasound technology is we're continuously monitoring the bearing friction. So we're fundamentally answering two questions. These are the same two questions that Rich brought up earlier was know when grease is required. So when we see an increase of that friction, and the question is, well, how much does that friction or how much does that ultrasound, and we measure ultrasound in decibels, how much does that have to increase? Right. And we'll answer that on the next slide here. So we know based on ISO standard of when the increase is related to lubrication or likely related to lubrication and when it's, a defect beyond lubrication. And we have tons of case studies we can dive into and go look at that. But not only are we knowing how much or when grease is required because that increase of friction, is we know precisely how much is required because we're trying to restore that friction back to its ideal friction level. It's something you're going to hear us refer to as the baseline, as that ideal friction in that bearing. And how you determine that ideal friction is a conversation on its own. But essentially, if you look at this light blue line, that's that friction going up. Now, traditionally, we try to catch that with this system very early on. The first sign that it needs lubrication, the system will kick in and automatically start to lubricate very, very slowly. And in fact, we had to do some things on this demo. So you didn't have to sit here for 45 minutes to watch looks like maybe a 2-inch, 3-inch pillow block bearing split housing lubricate. So it's going to do it very, very slowly. Right. Whereas traditionally, if we do based on the conditions, based on those variables, we often get to it too late. Or if we start to over lubricate, in fact, that light blue trend actually just keeps on compounding and compounding. So as we look at the friction part, a lack of lubrication will cause an increase of friction. A bearing defect will cause an increase of friction. But also if that bearing becomes over lubricated, now this setup here, it's an open bearing, so they're open on both sides, I believe. So it's very difficult to really extremely over lubricate. But in a lot of cases, when you start to over lubricate, you get into that hydrodynamic domain and you start to actually increase that friction. You have grease going different ways and it's trying to push it around. So we can detect under lubrication, a bearing defect, as well as over lubrication. And that's the power of the system. And then maybe Rich, you can just go. Oh, sorry, you got a question?
Yeah, I'll comment on that. This system here, you're exactly right. There are openings on either side of the housing where the shaft goes through, and we've actually removed the typical shields or seals that would go there to try to make sure they're not interfering with the testing that we're doing. So it's going to be impossible. And not to take anything away from the manual greasing approach using ultrasound in the field, but back to the study that we did with EPRI years ago, we said that using ultrasound as part of a rounds or route to give that data kind of feedback in the field to the lubricators is great, and certainly enhancement on not having it. But there is this thing where a certain amount of time might go by in an under lubricated condition before the ultrasound is detected manually, and then the grease is added. And so as you introduce us here to a real-time system, you can see how that interval is really shortened to the lowest period possible, so that, as you said, very early when that first increase in friction occurs, you're acting at that point in time here with an automatic system.
Yeah, it was interesting. As I said, I personally was humbled by the data we started to see. And I'm not sure why I thought differently, but what we started to see is when we put these systems out there is it was asking, or, I would say the bearing was asking for grease a lot more frequent than I thought it would. But I was like, oh my gosh, we're going to end up using more grease. But that was just naive thinking. What happened is, it asked for grease a lot more frequently, but the quantity was so much less. In fact, the lubricator, and we'll show you what the system looks like, the lubricator, the minimum it puts out is 0.33 cc, so a third of a cc, or a third of a gram if you want to word that over. So it's so small, but sometimes, especially as we get to pillow block bearings and things like that, that's all that's required. It will just I need a little bit of grease, and just put a dab in, and it's happy. You just see that friction start to drop. And I was like, oh my gosh, that's all it needed, right? But it needed it more frequently. So it's putting it in more frequently, but less quantity. And that's something that surprised me.
Yeah, and we often talk about that as someone who's been doing audits for years, and for some 30 years now, where we're going in and trying to take someone to a higher level of performance. That's kind of a principle that's always been out there, which is it's better to put less in more often than it is to put a whole lot in at once for a very long time for that machine. It's just kind of a fundamental maintenance environment in a facility, just not a thing that's well supported by the traditional. I've got a CMMS and my work orders are coming out and things like that, and I'm working on this machine, and then I might not see that machine for a very long period of time. But what you observed with implementation of a system like this tells us that idea that less more often is better than more less often is kind of borne out.
I should have talked to you earlier, Rich. Is that what you're saying?
No. I mean, it's great, and I think these things take time, and I think all along we've been, by using these technologies and using good principles, we've been incrementally improving lubrication, and I think this is just another step to get us closer to optimal, which is great.
Excellent. Let me go to that next slide. I'll quickly go over. So how do we determine what is that increase of that friction or that decibel? And I will interchange ultrasound and friction during this conversation, and then I do it not on purpose, but it is directive on purpose. So this is an ISO standard, and what it states is once you have that baseline, an 8 decibel increase indicates a lack of lubrication. Now, as I said, there's other things that can affect that friction. And if we see a 16 decibel increase, it indicates it's likely a damage to the bearing beyond lubrication. And 35 is critical failure. It's walking down the hallway, the temperature's hot and things like that. In fact, we have a bearing in this lab here that it's not quite at that stage, but it's definitely not a healthy bearing. An important thing to note is if you look for this, and maybe you can go to that next slide for me, Rich, and then I will ask if we're going to get into the live demo, Sloan, if we could start that machine up. We do have a bad bearing in there, so we don't want to run it through the whole demo. So maybe, Sloan, we could start that up just so we can get some data in. But we're going to start. We'll show you some live data coming in from these bearings, and on purpose, we have one that's needs lubrication. We have one that's completely dry, and we have one or two that are hand packed or lubricated. And what we're going to see here is a trend like this, and there'll be some other widgets that you'll start to see here. That green line, that dotted line on the bottom with the blue squiggly line, is that's the baseline, right? So this is that blue line is that friction we're measuring for a 24-hour period. That green is the baseline. So this is where ideally we want to see this. Now you might see some peaks and valleys, or you will see some peaks and valleys in that blue trend, and that's normal. There's no such thing as a perfectly smooth bearing. There's always going to be slight increases in friction, things like that, load changes. That blue dotted line, that's our lubrication level. That's 8 decibels over. And what's great about that is there's no such thing as a bearing that needs lubrication and somehow fixes itself other than needing lubrication. So it has to go above that blue line and stay there. And that's our sign that it needs lubrication. And then you can go in, you can lubricate it. You can lubricate it manually, or the system can lubricate it for you, restoring to that baseline. That yellow line is the warning. So if it goes above there, then you're starting to have some issues. Now you can wait for that lubrication to hit that level and then try to restore it, but you might be putting some secondary damage into that bearing. And that red, we don't see it too often, but unfortunately we do. It's not in a good state. And we've seen it where you can use grease as a means to nurse your way through failure, if that makes sense. To try to control it, you are going to use a lot of grease. You're going to, not be effective with that or efficient with that grease, but you can kind of nurse yourself through failure from that perspective. So this is what ideal looks like. This is an example from a fan bearing in an air handler unit.
Let me seize on that point that you just made there in terms of using a system like this to be able to kind of help along a bearing.
Yeah, exactly.
Triage it a little bit.
Yep.
And I want to take you for a moment to some work that I've seen being done by Poseidon Systems. And Poseidon Systems develops oil online sensors. So there's some parallels here. And they're doing a lot of work in the wind industry. And I was at a conference a while back and for a presentation, and I thought I kind of knew what to expect from it. And then Mark Redding went into how not only are they using the sensors there to kind of predict issues and so forth, they were actually using the information from the progression of wear to define the condition of the bearing with extent to how much longer can it go, and then changing the operating conditions, basically like reducing the load, right? Reducing the speed, because what they're trying to do there is get the point where it's a lower cost maintenance evolution and continue to make power, maybe less power, but make power up to that point. So the total outcome from that for that asset owner is huge. And until you just mentioned it now, I'd never really thought about an equivalent to that approach on the grease side. So it's kind of cool to hear you talk about that. Have you been doing that at all? Or is this more like something we could probably try to do at some point on the grease side as well?
No, we see it all the time where people will essentially this friction level becomes their set point for the load. So they'll okay, we're running at this speed, we're up high. We take it down here. This is kind of our sweet spot. So unfortunately, we do see it. It's not good for the end user,
Right.
but we definitely do see it for sure.
But it could be a situation where if that asset owner, that end user, has a critical period of production, and they can get through that either by adjusting the operating conditions and seeing in real time how that affects the damage progression of the bearing, or use the greasing as we know that you're not buying yourself much time, but there might be a short interval where there's an enhancement aspect to changing the feed rate of the grease. That could be pretty significant in some operating environments for certain assets.
No, exactly. And we do see it. And it's saying, it doesn't buy you a lot of time, but it can buy you a little bit, enough to get to, and where we see it the most, Rich, is pharmaceutical manufacturing. In particular, air handler units, because if they lose those, they lose sterility in the rooms, they lose millions of dollars of batches, and they will do everything they can to keep it running to the end of that batch.
Yes, something additionally comes to mind for me too. If you had a bearing where its sealing capacity was compromised, let's say, and you're in a say a high moisture environment or a high dust operating environment, that you actually are using a system like this to flush grease out optimally, right? To keep
So,
those contaminants
Chris,
at bay.
that is so. We had that exact situation. And I won't go into details. I could include it in the slide deck. If anyone wants to hear it, just reach out. But it's the same thing where we had it was moisture contamination into the bearing, and they used grease to purge out that moisture from the bearing, and we saw that friction drop. And even I was looking at it remotely because it was nowhere near me, and the customer said, I'm going to push grease in there and see what happens. And we saw that friction start to drop. I'm like, oh my gosh. So that's it. We've only seen one case of that I've seen personally, but that's really interesting. You brought that up.
Yeah, that's great. Next slide.
Yeah, if you go to the next slide. And thank you, Sloan, for starting that. So what we're going to see here is, again, that slide before was the ideal, right? This is what it looks like when a bearing needs, and this is an air handler unit, when a bearing needs grease. So you can see it go above that 8 decibels, it stays there. And if you were to reference that previous slide, this becomes a lot more, start seeing a lot more impacting. So the first thing we actually see is impacting, then the decibels start to go up. So to give you an idea, the on-track system is sampling the friction data from each bearing, and the on-track can monitor 16 independent bearings and lubricate 16 independent bearings. So it's doing this, is asking for that bearing friction or measuring that bearing friction at the rate of once per minute. So we get very, very granular when you think about an online system. So we start to see impacting, and we've picked up things like loose belts and things like that will show up in friction. But you notice here, when the user went to go lubricate, and there's a mode where I call it human in the loop. So it gives you an alert. It'll send you a text message saying, hey, bearing 101 and 800 needs lubrication. And you say, okay, go lubricate. And there's also a fully automatic mode where it will just say, hey, bearing 101 needs grease, I'm lubricating, right? And it becomes a trust thing and things like that. So there's different methods of doing it. So by the time the customer went to this, and that 8 decibels doesn't mean, and people, it's interesting because we've seen people move from, I used to grease this motor once every year, to, if I get an alert, I can't wait till the next morning to lubricate. And it's interesting. I said, well, you were going to wait another 8 months before you lubricated, but you can't wait till you get back into the office. And I'm not encouraging anybody to do it. We have one story of a person trying to put their son to bed, got the alert, was reading their kid, said, okay, go ahead and lubricate, read the book, fell asleep as most dads do, and then woke up and everything was perfect, right? I'm not encouraging anyone to do that, but it gives you the intent of the system. So the time this customer went and lubricated, they said, okay, go lubricate. And you can see that friction drop. That's what we want to see. Now, if you look at this, the reason it's so concentrated is, and this is unique with our system, is even though a minute seems like a lot of data, when you're lubricating, it's like watching a pot boil. You're like, right? So what we did is we send a signal just to that sensor. It's going to, instead of updating every minute, it's going to update every second. So it's like we're standing right beside there. And what's unique about that is whether that single point lubricator is mounted directly on the bearing, or we use remote grease lines to lubricate it, which we do have in this setup, is when grease goes and enters that bearing, as those rolling mounts are going around, we will see a momentary increase in friction, right? Because it's got to get through there, and the rolling mounts have to push it around depending the type, right? So we want to see that real feedback as grease is hitting the bearing. So anywhere in the world, we can actually make sure that that lubricator is actually lubricating through that grease line into there. And we see that friction drop. And sometimes it takes a few iterations. So it might put in a gram at a time, an ounce at a time, cc at a time, whatever it is. It might start putting grease in. And then it takes 1 or 2 times before we start to see that friction just to drop. But once it starts to drop, oh my gosh, does it drop quickly. And as I said, it can take 45 minutes to lubricate a bearing because it does it very methodically, and it's going to show you every step of the way. On the right-hand side where the second arrow is pointing, one thing we do, and it's very obvious, is we record all the information about when it was lubricated, how much grease was used, what mode was used, who gave it permission to grease, what the baseline friction was, what the starting friction was. So The baseline is what we're trying to get to. In this case, it's 11. The starting friction was 22.1, and it ends. So it automatically ends when it's in 2 decibels. And you can change it, but we found that's a sweet spot. We don't want to get too greedy. Get down to 2 decibels because it is going to fluctuate. As you see in this trend here, it will automatically stop. So as it goes back to reporting, grease analysis, cost savings, and now, as Rich mentioned, sustainability, you can start to map your carbon footprint. Hey, we used to lubricate this, 3 tubes every year, but now we're only using 9 cc's every 6 months or whatever it is, right? So that gives you an idea of how this system works. And of course, one more quick note here, we do talk to that lubricator, if you will, since we control it, we know the level of it. So no matter where you are on your smartphone, tablet, we're starting to see a lot of companies put these in big screen TVs up in maintenance shops. You can see how much grease level you have left in that lubricator, right? So I always say that if you run out of grease, you have chosen to run out of grease. You you ignore the alerts. In fact, the system won't even let you grease if this is empty. It's going to say, hey, I have no grease. And there's a number of checkpoints in place around the bearing capacity and things like that. Even if the friction doesn't drop, it's not going to sit there and shove grease into a bearing thinking it's going to drop. So you won't just empty a whole cartridge on a bearing. And the one thing I do want to cover, just really quickly, Rich, before getting the live demo, if you do have a defect in the bearing, you will not see a nice smooth drop like this. You might see a drop, but what happens is if there's a defect, and I use the analogy of you're filling a pothole, right? Is the grease might fill that pothole, but as those rolling elements go around, you're going to expose it. You're going to get the grease out of there. You'll see that friction drop. It likely won't drop to baseline. Sometimes it does, but that friction will come back, and we will alert you saying there's a potential anomaly detected in that case. Did you want to go over to the demo, Rich? Hope we didn't see you. Maybe I can't hear you, Rich, if you are talking. Maybe Tim, you could share your screen for me. Perfect. Thank you, Tim. And I'll do a quick introduction. Tim Going is our head of commissioning for UE Systems. He goes around and does these commissioning. So he's seen a lot of this data, a lot of these sensors. So I'll quickly walk through, and Tim, you're more than welcome to join, but and comment if you need to, or Rich. But just to give you an idea, so what we see on here is this is the friction level on one trend. Now you can customize these trends to show one, to show them all, things like that. But this is real data coming in from this system. So if you look at the top legend, sensor number 5, this is the blue here. And what we're seeing down here is this blue. If you notice, it's a little bit below. And because this bearing skid, and Rich, you can jump in here, is essentially a motor spinning a shaft on 2 pillow blocks. There's really no load, right? So we're not going to see a huge decrease in that friction because there's no load. If we were to put a load, it'd be changed. And because it's an open bearing, we're not going to see a big drop. But you can see this blue here is this is the sensor that needs lubrication. Sensor number, I think it's 6 and 3 are the ones that are lubricated, and sensor number 4, this guy right here, this is the dry sensor. So even just looking at this and understanding that maybe this audience doesn't understand ultrasound and how we're measuring it, just look at it from a friction point of view. If you were to put this system on and just look at everything's created equal, these are the same bearing housing, same bearing, same speed, which they are right now, which bearing has an issue? Right, this one's at around 42 decibels, somewhere in there, and the rest of them are down here, right? So undoubtedly, and I think, Rich, this one's actually physically hot, so that's why we don't want to run this too long.
Yeah, if I could, I think knowing a little bit about this, why we have an outlier like this, and funny, years ago when we built this test stand, I'm like, the bad part is all the bearings look beautiful, so I don't really have a bad case. Well, apparently we created a bad case, and Ron Jansen, who used to work with me at Peach Bottom Atomic Power Station, he's now working with us, and he found a bearing the other day that had slid. The fit on the inner bearing had moved, and he replaced that bearing, but apparently when they lost that axial control, it also damaged this other bearing. So when we got things set up with you here, we were able to find that issue. So yeah, it is indeed a damaged bearing that we're soon going to be replacing. But it's, you know, it's interesting to see that now as another data point.
Exactly, and it becomes so obvious. And I've looked at thousands of data points, and it's actually my simple joy in life is to see bad bearings, and it, you know, at the cost of customers, I'm sorry, but it's just always interesting to be able to see, like, you know, this doesn't look right. And if you just look at these trends, look at the impacting, the variation in that green trend of that bad bearing. Right now, we're not saying it's shifted its axis and things like that, but just looking at it holistically, you say this bearing is not right compared to the others. Right, it becomes very simple from a time series trend to look at. So, Tim, if you could scroll down, I think we're going to lubricate from the next screen down here. And this is UE Insights. So this is our platform. This is what you see live. It works on a tablet, your computer, a cell phone. There's no software to install, so it becomes very intuitive to use, and you can customize it. This is the way we typically set it up. So this is bearing number 5 on this skid that was intentionally left dry. Okay, so we can see the impacting and things like that. Slightly above baseline. As I said, it's an open bearing, so we're not going to see it drop too much. But what we're going to see here is, if you could, Tim, go ahead and start an assist cycle for us. So what it's going to do is it's going to ask us for our password, so you can't inadvertently pocket grease a bearing, which I never thought would be a thing, right? But here we are. You know, you pocket dial people. You don't want to pocket lubricate it. So what it's doing, and I'm in Canada, Tim's in somewhere in the south, right? Nowhere near your lab, Rich. And what's the point here? And what's happening here is he's initiating a cycle from Oklahoma, and what he's doing is he's sending a signal to the cloud, from the cloud to this on-track gateway, saying, hey, I would like to lubricate this. So since we update every minute, it's going to take a minute for it to, up to a minute, sometimes a little bit longer, for it to gather the request and go through it. So the first thing we just did here is, you'll notice we tried to lubricate. We said, okay, go lubricate. It gave us an error. Why did it give us an error? Because the friction right now is within its baseline. So it's essentially, if it was a little meaner, it would say, hey, dummy, you don't need to lubricate, right? So we tried to take all the guesswork out of it. And you can imagine if the grease pack was empty, right? It would say, I know you want to lubricate, but I got no grease, right? So there's all these different messages, right? And you can put, you can't grease more than X amount. So if it does try to grease and you've filled up the cavity, it will stop it as well. So what Tim did is he went through and adjusted that baseline. So the baseline is not going to exactly match. In fact, like this bearing, because of its conditions, doesn't follow that 8, 16, 35 decibels. Okay, so what it's going to do here is it's lubricating right now. So I'm going to ask you to keep an eye on this gauge widget that says 15.1. It looks like a gas widget. And also, you can see it start to move. Okay, and also, you can see this, it's lubricating. So it sent a command. It's waiting for that command to come back from the lubricator and saying, okay, I put grease in. Okay. As it's going through, it's putting 2 cc's in at the rate of 1/3 of a cc. So it's going to do it 6 times. It's going to go, bah, and it's a positive displacement pump. It's going to put a little bit of grease in. It's going to wait a couple seconds, put in more. And what we're going to start to see as this is lubricating, once it's done, is we'll start to see the impact of this grease hitting that bearing. Now, we did our best to prime this, right? This is a lab environment, so it may take, and Rich, you can go into probably more detail, some grease to fill the housing first before it actually hits the bearing. So we might not see an immediate drop as we normally do in situations like that. I don't know, Rich, if you want to add some context.
Yeah, well, let me ask an actual important question right now, because I guess bearing 4 here, we started with it dry. And Sloan was just asking, can we shut that shaft down? I don't know if you're monitoring bearing 4 right now.
Yeah, you can shut 4 down, absolutely.
Okay, so
as long as it doesn't affect 5.
it shouldn't. 3 and 4 are on one shaft, and 5 and 6 are on another. So
yeah, absolutely.
She should have the word there to move ahead with that.
Yes, and thank you, Sloan. I don't want to kill that bearing.
Yeah, exactly. I mean, that would be bad while we're trying to demonstrate the values of this.
To someone run by with the
lubricant starve one of our bearings, but no, it's yeah. So go ahead forward there, Blair, did you have a specific question for me
Well,
about?
just maybe go into details of why we have to fill that housing just by the design of it.
Oh yeah, so these particular housings, they're kind of a unique or different kind of housing where it's not a typical pillow block, which has a dual row. A lot of times they're going to be like dual row spherical roller bearings with W33 groove, and then a center grease delivery that goes right through the outer race and in through the bearing. These are straight back bearings like you would see in an electric motor application. And then, of course, the housing obviously is a kind of a straight bore, and then the grease gets delivered to the side of the bearing. So here, what's happening is when that grease is being delivered, first off, you have to have a primed line up to the point where grease enters the housing, and then it's going to lay that grease right in front of the bearing. So sometimes you have to build up a little mound of grease, if you will, that's along the face of the bearing before new grease being added is actually going to contribute into the raceways. And this is actually more similar to what you see in electric motor applications. So this is more like an electric motor shaft simulator that happens to be held by pillow block bearings.
Excellent. Way better job describing that than I would have, Rich.
No problem.
So what we're seeing here is that real time down to the second friction level. So you can see it's bouncing around, and it may take 2 iterations. So you can see on what we call the status widget, it says waiting. So it said lubricating. So it put grease in there. What it's doing is just patiently waiting. It's waiting to see if that friction is going to change and if it's going to need to put more grease in. So as we're waiting, it's going to count down, and that time is 5 minutes. And there's a reason it's 5 minutes, but that we find that gives an adequate time to make sure grease is going to circulate, get through the housing, get through there. So we're going to wait for that to count down, do one more iteration, and hopefully we'll start to see that friction really start to drop. Again, we might see a drop maybe 3 to 5 decibels. It's not going to be our typical drop just because of this setup. And what I'm going to ask you to do, Tim, if you could just click on the average value, that blue line on that widget for me, and I'll talk a little bit what this is. And maybe you could hide the red one for me, Tim, just so we could discuss this. So one of the things is because we're taking the samples so quick, we're taking it every second, we are going to pick up peaks and valleys, right? We're going to pick it up. We're going to pick up grease hitting that bearing, going through the housing. So one thing we do in the software platform is we take that raw data and we average it. We use a moving average. It smooths out some of those bumps, and we can change, how many samples in a moving average is. But we like to look at this, and oftentimes we'll hide the raw data and just show this moving average because it looks smoother, and it is it shows that drop better. So I just wanted to make you aware that we have 2 ways of kind of measuring this. So we're down to a minute here. This is the watching a pot boil. Thank you. So we can start to see here, our baseline friction is 0. So, and we actually do put it to 0 sometimes when we're commissioning, just to see how low we can get that number if we know the conditions of the bearings and things like that. So our starting friction was 14.6. Our last interval friction was 14.6. So we've only done one interval. We've only put in grease. We put in 2 cc's at one time. So that's what we count as one interval. And our current friction level is 14.7. So we haven't changed that friction yet. But I imagine here in 26 seconds, as we put more grease into it, we'll start to see that that number come back. Oh, I think we lost the live screen there. It went back to the slideshow there, Rich. I don't know, Tim, if you have to reshare or not.
Yeah, I saw it there for a moment, and then it disappeared for me too.
Okay, we're back.
There we go. Super.
Perfect. Thanks, Tim. Okay, 12:47. So we're going to wait. So it made that decision because we have our baseline set at 0. It's saying, hey, I'm still not at my my baseline friction. I haven't reached the max capacity of that bearing. So I'm going to lubricate again, right? And it's making all that logic for you. So right now, grease is entering that bearing. If you zoom into this, we probably would have seen this, or someone caught it with their eyes. Where that gauge widget where it said 14.4, it probably went up to 17, somewhere in there as grease hit the bearing and went over to the right. And then hopefully we'll start to see this drop down to the left here. And again, you start to see how this system works. And actually, one thing you would have started to see is um, the lubrication level starting to go down and things like that. And then below this one, you can see the last time we just did this morning just to make sure. I think Sloan MRG did it, just lubricated this morning just to prime everything if as much as we could. So she put in 2 cc, so we can go back through any point in history. So again, we're pushing grease through, we're pushing it in slowly, so we're not expecting. I am seeing some drops here on the right side start to go down. If you take a look at the average, Tim, are we seeing that trend go down at all? Right, so we might start to see this start to go down as grease hitting the bearing. And this is the waiting game of lubrication, right? And I think it gives a good analogy though, is as you're applying grease, and we have some videos that we use of people using ultrasound guided lubrication or handhelds, but then they're pumping grease in like this, right, as fast as you can, right? So it kind of shows you how really methodical, if you would, if that's the right word, how you should be putting grease into a bearing, and the system does it for you. So we're sitting here watching paint dry. I understand that, but hopefully we'll start to see this level go down. But it depends on that bearing. We did see it as we piloted it last week, but conditions could have changed here.
Yeah, that's you raise a good point there, and it's another thing as we look to advise people and do audits and you look at existing greasing practices. That rapid pumping, like how quickly can I finish this route, is not good for machinery. And so you raise a good point here. You've designed a system that carefully evaluates the response, because it's not an immediate response. And this is another reason, Blair, why I think we end up defaulting to over lubrication, right? Because there's this desire for immediate gratification or immediate feedback of I'm pumping this thing, what's going to happen here. And it takes time for grease to move. Grease is it's a non-Newtonian fluid. It's not a hydraulic medium. It doesn't become the same pressure everywhere in the system all at once. It has pockets of pressure that must slowly be relieved into the surrounding material. So this kind of slowness of response is quite expected. It's physics, and we shouldn't try to rush physics, right? We should have a system and an approach to lubrication that reflects that it takes some time for grease to move and grease to function. And then for reasons that we just talked about, the specific design of this bearing housing, there's other factors at play that may delay the delivery of the grease truly to the raceway into some kind of change in measurable condition, even make that a little bit of a more delay. And we knew that was a possibility here, right? That's why.
I think one more time is probably going to do it. But what we could do, Rich, is we can move over to sampling if you want. Let this run. I guess you're probably take it off of the skid though, right? So we need to shut down.
Yeah. So I think, and so I believe Sloan is still listening in here, and Megan as well. I think that we're working the operator bearings are on the left side of our skid, so we could keep that door closed and then maybe look at things on the right side. We'd have to get the feedback for that to work. If we wanted to demonstrate and show sampling taking place, though, you're right. We'll have to turn the unit off to be able to access that.
Yeah. So I was just going to jump in. So we're only working on bearings 3 through 6 for this demo. So bearings 1, 2, 7, and 8 are currently not greased, and they're completely clean. They're not being used. I just shut down though
3 and 4,
5 and 6. So that all 4 of those are available, except obviously 4 is totally dry.
I can see it on screen.
Yeah, we can tell because either the grease. Well, this actually worked out well, so because you can see here, it was done right before it was making that decision to lubricate again. So it said, "Hey, I'm at baseline." We set our baseline to 0. It said, "Hey, friction levels within 2B. We reached it, right?"
Can you blow up that last data point where you can kind of see that it was indeed kind of dropping right before Sloan turned that off? I think there's like a last data point there that's pretty much lower than where it had been. So it looks to me like maybe some grease was getting in there. And this happens too, Blair, right? That sometimes grease gets in, a little grease gets in, and kind of gets flung out, and then so sometimes you go down a little bit, up again, and then down again. And this is part of that patience of response that this kind of system like this affords, or, someone using ultrasound, it gives them the opportunity to kind of have some patience, listen, make sure that drop is sustained drop in the decibel levels.
Exactly.
To take it to the pilot data so you can have an idea of what that looked like.
Yeah, absolutely. If you want to show this, what it looked like. And I think we had to put a few iterations of grease in there. So this was, I think, last week. Right.
Look at that.
Yeah. Right. So you can see that friction drop right there where his cursor is. A little grease was added. So what was that? Maybe 3 or 4 decibel drop. Right. We can see it. And you can also see the start of the impacting, just those outliers on the top and bottom of when it needed grease to how more condensed it was when grease was added.
Yeah, the left side plateau versus the right side plateau there. There's the difference in how much impacting is there and how that's diminished when you have that. I don't know if you want to call it a damping effect, but you've got more grease there.
Exactly.
Yeah.
Excellent. Thank you, Tim.
That's great. I think as Sloan is looking to restore the video feed to those bearings so we can watch them pull the cover, I'm just going to go to the slides we had and just show real quick the sampling and analysis options that are here, and then we'll finish up with actually seeing them pulling some samples here, I think, in a minute. But here on screen now, I have some of the different kits. The Grease Thief is a device that complies with ASTM standard D7718, which is the in-service grease sampling standard practice. And it involves, looking at the proper approach, methods, and tools that are necessary to obtain a representative grease sample. Grease is more challenging to sample than oils because it's designed to stick. It's designed to stay in place. So it's not just a matter of opening up a valve and letting it run out, or pulling some suction and hoping the grease flows into whatever vessel you have. So the Grease Thief is a solution for that. It involves, in some cases, actively coring the grease, much like you would core a soil sample, or in some cases, passively collecting grease that is exiting from the housing before it becomes contaminated with the surroundings. So you can see some of the kits here. Pillow block, obviously, that's what we're using today for this demo. Electric motor, gearbox applications, robots, wind turbines, and then a device that we devised for getting into very, very small openings down to about 8 millimeters in diameter. That's the Grease Thief Slim. So there's those tools out there. We're going to demonstrate, hopefully here in just a moment, if we can get that video feedback on the disassembly and then the use of the pillow block kit. And then what do we do with that sample? Then it's the analysis techniques that are outlined in 7918. So when it comes to combining this real-time use of ultrasound to optimize grease delivery, as well as the secondary monitoring of the condition of the bearing that Blair was able to share with us here. You also have these other elements that are related to the chemistry, contaminant levels, and also the wear levels that we find in greases, and they're encapsulated in this one standard, which is ASTM D7918, that allows up to 10 different tests to be performed on the grease. That's just 1 gram sample. And so, yeah, great, perfect timing, and we go right to the live feed here. So I have it up on my main screen. Does everybody else see that?
I can see it on my end, and Megan's the one sharing it, so
perfect.
I think we should be able to. And we're going to sample from this one because it's cooled down enough. And I hand packed this, so it's a little bit different, but just so you guys know, we're going to sample from this as the back is still cooling down. So I already went ahead and took the bolts off. I just pop it up.
And for those watching at home, we have a lockout tagout procedure. So our system is locked out, and this is a split housing. Again, I say this is not a typical pillow block arrangement, but again, they're just going to have to loosen that up and then get a lift off of the upper, the top half of that bearing with the bolts having already been removed. And then what you'll see then is the fact that the housing has a flat bore, and the flat bore allows then in this case, the bearing has spacer rings on either side. And that means this is the locked bearing versus the floating end. So this is the fixed end versus the floating end. And so as you get the thermal growth of the bearing, the second housing at the other end of the shaft is going to be able to grow in either direction. But here, this is the fixed end. So you can see those two rings. So you see kind of three circular pieces there on the housing that came off. And you've got the two fixed end rings. And then in the center there is that bearing, the flat surface of the outer race. And now what we're doing is opening up the pillow block kit that I showed you, extracting a spatula. And what we usually do is the spatula has a wide end and a narrow end, and we usually use the wide end to kind of move away some of the grease that's peripheral to the bearing itself, and then spin it around. And now we can reach in to the area adjacent to the bearings rollers themselves to extract the grease. When we get that out, it's going to be packed into a syringe. That syringe is opened by removing the plunger. And so we have an open end into which we can pack the grease. Some folks believe or think that, the grease has to come from under the rollers specifically, and then everything else is just, packed in grease or whatever. What we find in practice, however, is that a greased bearing, as it heats up, and as you get this shearing motion or the movement of the bearing in contact with the grease, drags grease along with it, and it creates a more fluid-like state. So you get a small area of grease close to that moving parts of the bearing that move around with it, that mix with it, and become part of the system that is then representative of the grease that's lubricating the bearing and any particulate contaminants, et cetera, that are present. So that's what we endeavor to do. We get in along the face of the bearing, not necessarily digging under rollers, but in that face area, and extract that sample out. And when we have enough, which is the target is around a gram of grease, we then can put that plunger back into place, and then get out the grease thief and then transfer the grease that we've captured into it. By the way, this housing here, or this test stand that you're seeing close up right now, is part of something that we use for different research projects, including grease compatibility studies. And so this has been an issue that was a challenge over the last 2 or 3 years or so, with supply chain issues and so forth, interruption of grease supply due to fires and all kinds of crazy things, where some folks are faced having to switch from one grease to another. And so this is a stand where we can actually put mixtures of different greases together and test how they work over a period of time in a mixture, in a bearing together. And this is part of how we test it. So you can see the grease. Now it's going to be transferred from the syringe into the grease thief. Again, we're targeting that 1 gram of grease, and we can do a whole series of tests once that's been obtained. So that's our grease sampling process. And as we said, that's another element that gives us insight into this kind of condition monitoring approach. And if we monitor the condition of the grease, monitor the condition of the bearing, we really can work towards grease optimization. There's our sample, and we're ready to walk it 2 feet away to the laboratory where it could be tested. Blair, that's kind of what I wanted to cover today. I want to turn it back to you to see if you had any more thoughts or comments on this before we close out.
No, and I think hopefully this is just part 1 of a series we could do, Rich. So I think there's a lot we could do with your lab and our technology. And as I said, we do have some exciting new features coming out too. And I think this system would be a great one to highlight that on. So thank you for the time. This is fantastic.
Absolutely. So thank you to Blair for joining us today, for showing and sharing their system for monitoring and controlling grease delivery in real time to bearing systems like this. And thanks to the MRG team, to Sloan and to Megan for helping out today. Every month we have Grease Thief Thursdays. we're Sloan, looking into July or
our next
wait.
is going to be August.
August.
And
Okay.
that is projected to be turbine oil monitoring, I believe.
Oh yeah, right. So moving out of grease and over to oil again, and I think we're going to do a few things there. One is to do some demonstrations of our new system that we have from Tanis for oxidation testing of turbine oils, and then also show some of the other capabilities that we've been doing for some time, which includes ruler testing, varnish testing, and so forth, and really how this kind of analysis from a lab is really benefited from having some folks that have experience in the field, and we do here. So look forward to that. If you have other ideas for things you'd like to see in the future, we'll definitely be bringing Blair back in the future to share some more things about their work around grease lubrication. But I would like to thank you for your time today. Thank you, Blair, and have a good rest of your day.
Thanks, Rich.